And without further ado, I'm going to hand this over to Brad and Ron.
Okay,
Thank you.
Thank you. Can everyone hear me? Is this thing working? Is the mic working? Nope. Can you hear me now? Okay. All right, well, it's great being here with you in Brick City. As I understand, we were in Brick City. I always thought of St. Louis as the capital of masonry. I know that y'all do a tremendous amount of production of masonry. But Ram and I are here to talk to you about something that's kind of a passion of ours, sheltering from danger. And we're going to talk about the differences between the FEMA P-361 ICC-500, which the ICC-500 is modeled after, and the DoD Shelter for Terrorism. This is quite interesting because the dynamism between these two shelters. But in today's increasingly unpredictable world, the design and construction of human shelters must address a range of hazards, from natural disasters, tornadoes, and hurricanes, to human threats, terrorism. I'm sure y'all are familiar with terrorism happening every day, it seems like now. We will look into the possibility of a shelter serving as both hazard types to address both hazards, earth-made and a man-made. With this, we'll also briefly discuss, for your own edification, a little bit about the architectural and mechanical similarities of each type so you have a better understanding. First of all, I'm Brad Russell. I have a long history with storm shelters and bomb shelters, but I'm a founding member of NSSA. And I got my original undergrad from Texas Tech with a civil structurals emphasis and an architectural degree. I went on about 10 years later, I came into Dallas and worked for about 10 years, and I decided to go get a master's of structural engineering from University of Texas at Arlington. And then about another 10 years later, I decided I had some good ideas. I decided to go pursue a PhD with SMU. And right now we're testing a couple of my patents on connections, which happen to serve masonry also for solving the force requirements due to earthquakes and high wind events. This is my associate, Ram Thapa. Why don't you give a little brief background on yourself, Ram?
Hi, everybody. My name is Ram Thapa. My name is Ram Thapa. I'm associate with Brad. I worked in FEMA for 5 years as a civil sensor specialist. I graduated from UT system, UT Tyler, in my bachelor degree and master degree in structure reserve. So we are both working so many center as a designer and third party designer. And most of we work school in Dallas area and Lubbock and other state too. Yeah, I'm very humble to come here, and thank you for sponsoring Rainer. Rainers before I saw, and thank you for National Institute for St. Louis giving opportunity to us. Whatever we research and we did and share with you guys.
Okay, thank you. Okay, so also, Allison, have you distributed the article or? Okay, so I have written an article on this presentation. If you'd like a copy, just reach out to Allison and she'll get you a copy, or you can give me a card and I'll send you a copy myself. But these are the learning objectives. We'll review the architectural and the structural similarities between both the storm shelter and the DoD Shelter for Terrorism. We will discuss between the architectural and structural requirements for shelter, and we will briefly talk about the architectural and mechanical engineering air circulation requirements. And finally, all of this will help us understand the differing requirements between the FEMA P-361, ICC-500, and other government regulated codes. There are numerous similarities in architectural and engineering requirements of storm shelter and a DoD shelter for terrorism, as well as specific differences. And we'll try to address all of it. Basically, we will do a high side image of both requirements, so you can get a good understanding. We will not be able to cover all the aspects of these shelter types because there's just too much to cover in this 1-hour presentation. But we will look into the steps so a building can serve as both types of shelters and discuss the similarities of a FEMA P-361 ICC-500 storm shelter and that of a DoD shelter for terrorism. These are the codes that will be applicable to this presentation. First of all, let me ask a question. Let me get a gauge of the room. How many architects are there in there? Wow, there's that's good. How many engineers? Wow, that's good too. How many code officials? Wow. How many people that work for cities? So how many of you are architects or engineers who work for the city also? I know that Eugene back there was one of them. Okay, that's a good assortment. So you're vaguely familiar or you're very familiar with these codes. True or not true? How many have designed storm shelters? Okay, how many have, as an architect, how many have engineered? How many have done performed third-party inspections? Okay, that's good allotment. So we will be following the ICC-500. The latest one is 2023, is showing up here. We'll also be following the ASCE 722. Just for reference, I'm on the ASCE 728 writing of the new code. It'll be issued in a couple of years. And I'm on specific on some of the committees for seismic, storm, hurricane, and tornado. Also, we'll be talking about FEMA. Any FEMA people in here? I've worked for FEMA before in the early 2000s. Rom just.
Yeah, I work in 2022, 2025.
Yeah, Rom spent the last 6 years with FEMA, and so. But also, we'll look at the Masonry Institute, Masonry Society. You're familiar with this, I'm sure, being a masonry location. And we'll look at the blast protection of buildings from ASCE. And finally, we'll dab into NFPA, fire protection, because of the blast situation. We'll look into NFP 101, which is basically the life safety code. It features that minimize the effects of fire and how to minimize the effects of fire and related hazards. It also is a document that covers life safety in both new and existing structures. We'll look at the AISC Design Guide 26, which is centered on design of blast-resistant structures, providing guidance for the design of blast-resistant structures and progressive collapse. It's more into progressive collapse. Okay, this shows, these are the codes of concern that we'll be talking about, and I'll briefly discuss these. These are primary sources of this discussion. The FEMA 361 is the code the ICC 500 is based. So ICC 500 just takes it a little bit further than the P361. The P361 sets the minimum standards for the design and construction of storm shelters. Both the tornado and hurricane shelters require structures to withstand high winds up to 200 plus mile an hour winds or higher, depending on the risk assessment. The aim is to create an environment that secures occupants that ensures occupants are shielded from external wind pressures and flying debris. You'll see in ICC 500 there's stipulation for 2x4 at 100 mile an hour penetration. The doors have to withstand this. The wall assembly has to withstand this. the windows even have to withstand that. Okay, again, these first two codes are based on the blast resistant structures, which we'll proceed into the storm shelter segment first, and then we'll get into the bomb shelter next. But these are based on Unified Facility Criteria, UFC, different segments of this. One is structures to resist effects of accidental explosions, and DoD minimum anti-terrorism standards for buildings. Mainly these affect, DoD affects government-related buildings and possibly chemical plants, but something that we're experiencing an explosion would be very detrimental to the population surrounding. Okay, so first, I assume most of you are familiar with the spatial requirements of a storm shelter, but let us discuss the architectural similarities between the FEMA and ICC and the DoD. Both the DoD and the FEMA ICC have short-term are identical. 5 square feet per occupant, 10 per square feet per wheelchair users, 30 per square feet for bedridden occupants. The key to storm shelter design, and especially shelter for terrorism, is redundancy. You'll see me. I'll be speaking about redundancy a lot in this session. Okay, and this is discussing the mechanical ventilation requirements that I said we'd discuss earlier. In addition, for both the FEMA, ICC, and the DoD, the mechanical circulation for short-term, again, is identical. For short-term occupancy is identical. The ICC-500 requires a minimum of 6 air changes per hour. For shelters occupied for 2 hours or less, which is the tornado shelter, should be at least 5 cubic feet per minute air circulation, ventilation. And also for shelters 2 hours or less, tornado shelters, the ventilation rate should be at least 5 or 6 square inches per person. And this is a plug and go. You know your occupancy level by the square footage, and so you'll work backwards from that. But the shelters for longer stay, for more than 2 hours, the ventilation rate is 15 cubic feet per person, or 8 to 12 square inches per person of ventilation. The residential is only 4 square inches per person. Also, the differences in the ventilation requirements between short-term, less than 2 hours, and long-term occupancy in storm shelters is due to several key factors. First obviously is the accumulation of CO2, which we all can imagine why this is required. A short-term shelter scenario, CO2 levels can remain within safe limits with a lower ventilation rate. 2, the humidity and comfort of the occupants. Higher ventilation rates help control humidity, which is especially important for shelters occupied for extended periods. Potential for psychological stress. People get in confined spaces and funny things happen. But a fresh air circulation can help reduce feelings of claustrophobia. Finally, health and safety reason. Extended shelter necessitates a higher level of air quality, which you be required to provide in your mechanical circulation. So the performance criteria for the ICC-500 and the P-361, this is not the DoD yet. The performance criteria between ICC-500 and the FEMA 361 and the ASC SCI 59, which is talking about bombs, bomb explosions, relate to their scope, intended applications, and specific design focuses. First of all, the scope and purpose, the ICC 500, P-361, the focuses are specifically aimed at the design and construction of storm shelters and safe rooms to protect against extreme wind events like tornadoes and hurricanes. The performance goals protect against wind speeds up to 250 miles an hour and impact resistance of flying debris and occupant survivability. On the bomb side, the ASE SCI 59, which addresses blast protection of buildings, the focus is designed for blast protection and mitigating risks associated with explosive hazards. The performance goals focus on protecting structures and occupants from blast loads. The design code considerations of the ICC 500 and the FEMA P-361 wind loads. The documents require design considerations for extreme wind loads. The impact loads, resistance to high-speed windborne debris, for instance, a 2x4 lumber that's 10 foot long at 100 miles an hour or more. It carries a significant force that the components of the shelter must resist impact of. Also, these shelters must resist overturning and uplift. We will see later on a shelter that was designed and built is under construction right now in West Texas and in the tornado, right dead center in the tornado alley, is how we address that, because you wouldn't imagine the wind loading on these structures. The tendency of the shelter to overturn is quite significant, as well as blow away. But you want to prevent sliding of the shelter, and overturning of the shelter, and obviously collapse of the shelter. Okay, so structural performance. We'll get to Rom here in a second, but do you have anything you want to add, Rom? Go back.
So that one, your design aspect. Yeah. I design most of system center design aspect. Let's talk about here in Texas. We have a lot of designers, but we have divisions on inspector and contractor. Most of South in Texas, uh, they are not in the field side. A lot of they don't really see much. And they just pointing. There. So we need more. I'm very here is I'm very happy. A lot of already hearing about masonry. Like he asked, before I'm asking some anybody here contractor side is available today. I'm attending this meeting. The contractor side and how about manufacturer side? No manufacturer. Oh, okay, manufacturer. Yeah, in Texas we need more manufacturer and contractor side. Okay, and field is more needed. Because when I design and sometimes I go to sites and they it is very hardly they understand about aspect. Let's go by slide. Yeah, this is all talking about structural performance. This is the ICC 500 and FEMA P-361. When I was working in FEMA, we have a lot of FEMA itself. We funded. We used to fund money, and then we need to review a lot of public center, schools, and colleges, and law enforcement officer, and like that. And that here is the two things: ACI 5922 and AISC design guide. It says talk about two things, energy absorption, ductility, anti-reflection, and damage criteria. If we, today we don't have much time. I know we go. If you look at, this SCI, all it has guidance. Yeah, that is about human factors is and we have at that slide one. this occupancy density, and that is ICC-500 FEMA. It's all about how people how the affect the sport density, how many people, the criteria they have, 3 to 5, 8, and more people, and up to 200 people like that. It's 500 is one. And another one I see SCSCI. Yeah, that is more talk about the blast, how to blast before the prevention of blast, and then after post blast recovery.
What?
We have
Go ahead.
doing that.
Yeah, we're going to get to that in a second. But what we're almost trying to focus on telling you is you need to really be involved in construction, because we get to the sites all the time, and 80% of the contractors out there can't speak English, and another 75% can't read the writings, and we're constantly finding things they're not doing correctly. And but that is very detailed oriented. And when I say redundancy, that's not only in the design side, but that's also on the construction side. So the redundancy protects somewhat against the failures of proper construction. But this is the project that I was speaking of earlier. Okay,
Yeah. I have design.
Okay. This is a project I was speaking of earlier. This is a sheriff's office 911 call center in West Texas that's right smack in the mid of the tornado alley that stretches in between Oklahoma and Texas. And actually, they've seen 2 tornadoes within a couple of miles of this facility being beat already this year. But this foundation, you can see the thickness and the strength of the foundation. You lost me. Can you hear me? Here, let me see that. So this foundation is definitely stiffened to prevent a couple of things. Prevent its overturning. This weight of this foundation is designed to also resist the overturning of the walls. This is going to be a CMU, a low-bearing wall storm shelter. The storm shelter itself is 1,200 square feet, but the sliding effect of the storm producing on the walls and the overturning effect of the foundation is resisted by this heaviness of the foundation. So we have to have something, and it's also it's paired with bell piers, so you got the effect of the weight of the soil above the pier. Can you hear me? I'm sorry. Okay, so you've got the weight of the soil above the bell piers. Do y'all understand this? I'm sure all the engineers do, because the cone effect of the loading of the soil above the piers act to hold down the piers and the structure above.
Yeah, this one is most of structural engineer based. Yeah, that's talking about, this is getting from FEMA books. That is just trying to say wind load direction. Yeah, this is wind load, how this goes. The particular horizontal direction and uplift direction. This is more an structural engineering aspect. Yeah, this is also from FEMA book. They have a very conservative design over here. And one is I need to give. This is the credit for that I get from one books. It's Andrew Stokow book. That is the left side that design. CMU for storm center design. That one. Here is we have designed Dallas. It's above grade storm shelter and below grade is CMU. this is the ICC wall. This is just showing that it is for residential project on North Dallas, Texas. This is which is currently under construction.
Okay, hang on before we go to these two shelters. These are residential shelters. They're CMU above grade and below grade that are resisting mainly the above grade is resisting wind load, and the below grade is mainly resisting the soil load. But that is the best place for a storm shelter to be located above below grade and in the proper soil type. Go ahead.
Yeah, that's similar. This website is similar above and below grade storm shelter. Right side. Okay. Oh, these one.
Go back. Okay. All right. Go ahead.
This is how do like above or below grade scheme this center. We have done in our project in Dallas, North Dallas. This project in Dallas, yeah, it is already completed.
No, it's under construction, but this is a storm shelter that's using CME for the shear force to take in the shear forces, but the exterior walls below grade were concrete. You can see on the both photographs show the CMU for the acting as shear and actually carrying the first level of concrete flooring. And then these, go ahead.
Yeah, this one is high school. This is grade. They are using for gymnasium on the event of any danger and all the students go inside. Yeah, this is all this needed. A lot of things we need to consider. Short-term sheltering and long-term sheltering, and then we have to look at it like we needed in each long-term sheltering. We need to have medical needs, center needs, and mostly it's ventilation. Before he talked about ventilation.
So this is getting into the DOD, but the previous two slides were the same project. One was under construction, and one was a portion of the project that had been finished. This here, we were getting into the DOD special requirements, and again, I know that the DOD and the storm shelters are both identical for short-term loading. But the DOD will address what we call a CBRN, which is chemical, biological, radiological, and nuclear protection. And this will be like chemical plants that I spoke of earlier. That the apartment building had a neighboring business that was located close enough to require storm bomb shelter requirements because it had chemical explosives. The DoD Unified Facilities Criteria, UFC, often refers to the National Fire Protection Association, which I showed you earlier of the reference, Life Safety Code, which specifies occupant load factors based on the type of occupancy. And it can range from 7 to 20 square feet per person per occupant. The DoD standards are designed with a focus on human threats, incorporating blast resistance, ballistic protection, and contamination control to protect against terrorism-related hazards. But then again, on the storm shelter side, the performance criteria for storm-protected buildings, which is outlined in ICC-500 and the FEMA P-361, limits structural collapse, maintains the building envelope, and minimizes impact of flying debris. As I spoke of earlier, the 2x4 at 100 miles an hour can produce a significant loading on the doors, the windows, and the wall system. Now let's look at this. This has me I saw this and I said, wow, these, the left side is a wind loading and the right side is explosive loading. And you can see both the positive loading of the explosion and the high wind loading are identical in shape. The right side, the graphs of these wind loadings and explosives are very similar. But the right side, we're getting into the DOD explosive loading. The positive force is above the atmospheric pressure is called the incident pressure. And this pressure from explosion rises above the atmospheric pressure due to the initial shock wave of the explosion. This portion of the graph represents the blast outward force exerting compressive stresses on structures and the objects in the vicinity of the explosion. The negative pressure, which can be more hindrance to the building, is a suction value of after the positive force is driven out of the area, creating a suction from the area behind it. After the initial shock wave from the explosion passes, a vacuum-like condition occurs, resulting in a pressure drop below atmospheric pressure. This phase represents the suction or under pressure that follows the initial blast wave. And it can also cause structural damage due to the rapid reversal of pressure. You've got a heavy positive pressure followed by heavy negative pressure, and it can be detrimental and be very highly effective and destroy the building. But then let's look at the ASE 59, which is the blast protection of buildings, and the AIC design guide, which is design of blast resistant buildings and petrochemical facilities, which I noted earlier is a highly explosive environment. The focus on both of these codes is to design for blast protection, meeting risk associated with explosive hazards in industrial and high-risk facilities. The applications primarily relevant to petrochemical facilities and government buildings exposed to blast risk. The performance goals focus on protecting structures and occupants from blast loads. It provides detailed guidance for blast resistance of building design. Did you have anything you want to add? Here we have a CMU bomb shelter, and we can see that it's got there's several ways. The loading, we'll see here in a few slides, the loading on blast forces is extreme. And the best way to design with CMU in that instance is to have a low grade structure and use the grade as an effective offsetting the forces, or have some sort of sacrificial areas that are absorbing the loading and collapsing. And right here we can see there's a CMU inner wall, but then there's some sort of other barrier on the outside of these structures. But the typical CMU bomb shelters are recessed below grade. There again, the architects will understand that when we recess a bomb shelter under grade, we still have to address the ADA and the MEP protection from CBRN. You have anything you want to add? Yeah.
Yeah, that one, yeah, CMU bomb shelter. Actually, it is a storm shelter, but we can make a similar in bomb shelter. It is supposed to get credit for that is iron shoal, and yeah, that is we have one book that I get from there.
Yeah, what he's saying is if we recess it below the grade, we can address both the bomb shelter and the storm shelter. because of the massing of the grade surrounding grade. Anything?
Yeah, all, but just designing a storm shelter, we supposed to consider a lot of other, so ADA compliance and MEP or fire code and.
Okay, so let's get into blast loads are typically given in KSI because of the extreme conditions rather than PSF, which is a typical wind loading. We will be looking at the next few slides. We'll be looking at a typical car bomb, which is 200 to 1,000 pounds of TNT. And we'll be looking at when blast loading is at an angle to the vertical elements, the blast loading on the surrounding might reach 25 times the initial blast loading due to reflective surfaces. We've got an incident wave, we've got a reflective wave, and then we've got the mock stem to deal with. So in a city environment, for instance, you've got a lot of hard structures around, and that the blast loading going off in a city environment, there's compounded pressures coming from all of these reflected surfaces that is making the blast loading extreme. So this is a slide that we're going to see a couple of times. And right now, I just selected a 1,000 pound TNT, which is a car bomb, and it's basically the maximum design car bomb, but it's not the maximum that we've seen in the last few years. But now I've got a 1,000 pound car bomb. I've got a 500 foot standoff, and I've got a 0 angle of incidence. That's taking no reflective surfaces coming in, adding into the loading. And we're comparing that to the wind load event of 250 mile an hour wind, essential facility, and again, a 0 angle of incidence. And they're both pressures, 1.8 PSI, where we can compare them, are the same. Again, we got a 1,000 pound TNT, 500 feet of standoff distance. That's a football field and a half away. That's huge. And we're going to see some others here that are even further. So right here, we recognize this, don't we? You recognize this? This was a car bomb. And it was 4,800 pound TNT. And I chose a 10-foot standoff distance because it was basically not under the building yet. It was basically on the edge of going underground when it went off. And I chose a 0 angle of incidence. And see the pressure, 20.94 KSI compared to 1.8 KSI. That little difference can make that big a difference in the loading of the building. And granted, it's almost 5 times the TNT loading, but the standoff distance was only 10 feet, and the angle of incidence was 0. And it got 21 KSI. That's crazy. So I've been talking about the incidence wave, the reflective wave, and the mock stem. This diagram shows what I'm saying. The incident wave is, if you can see my hands, is the bomb goes off, the incident wave goes like this. And then the reflective wave, if the bomb goes off above grade, and we've got another slide here, if the bomb goes off above grade, say 10 feet or 20 feet, and it goes out like this, incident wave, but then hits a solid surface on grade, like parking, then it's reflecting back up, and it's creating a mock stem on the sides. And then you've got added effects if we've got hard surface buildings, if it's in an alley or they've got hard surface buildings next to it, then we've got more reflected energy coming back, and compounding the effect of the explosion. So let's look at 1,000-pound TNT, 2 football fields. 2 football fields. That's a short wedge for you golfers. And then we've cut it down to we've created a 70 angle instance, and now we're looking at the same 1.8 psi, which is identical to the wind loading of 250-mile-an-hour winds, which is extreme. But I just want you to look at this and see. So we had earlier, we had 1,500 0 angle 1.8, and then we had 4,800 10 foot, and then we got 21 KSI, and then we've got 1,610 standoff and a 70 angle of incidence, and we get the same 1.8 psi, which is again compared to the high wind event. Any questions? Do you have any questions? Well, do you follow what I'm saying? Do you understand the angle of explosion to the hard surfaces creates a magnifying effect? The ground creates a magnifying effect. The Mach stem can create 25 times the initial bomb explosion instant wave. That's crazy. That's where we get this 21 KSI, and that was not even the worst that we can go. Do you have anything to add? Go ahead. You got a question?
21 KSI and then 1.8 KSI.
Yeah, right here. 20 KSI horizontal loading.
The other way is 1.8 KSI.
No, KSI. Oh, I got PPs. Oh, no, it is PSI, but I reduced it down, and so the difference in that is quite large. 21 KSI versus 1.8 PSI is quite large. Any other questions? This, yes, sir.
Talking about the items, and one of them, the last one,
Yeah, I'm talking about the Mach stem. Let me go back to the diagram. Here, we'll get to another diagram here in a second. The Mach stem is that vertical line between the instant wave and the reflected wave. And the intersection of these three is called the triple point. And what happens is the instant wave, which goes out, radiates out, and then the reflective wave, they coincide. And well, I've got another slide here in a few minutes, and create a Mach stem, which can be 25 times. And it's a matter of, it's like this. I was thinking this morning, where it's kind of like you throwing a pebble over here in the water and a pebble over here in the water, and the waves interact. The waves circulating from the pebble, you follow me? They interact in the middle here, and that's what creates the Mach stem, and versus it's water versus wind or air. You follow me? You say do you understand? I'm okay, because the Mach stem is a creation of the instant wave and the reflective wave combining to create a heavier loading on the structure. So we talked about this. So the explosive loading produces shock waves of high pressure, and loading decreases rapidly with distance. The best design mechanism for these blast loadings is distance. There's other options. We can create layers. We can create layers of failure modes. But the best way to prevent these effects of blast loading is for distance. And this diagram shows you the bomb shelter, a masonry bomb shelter on the left, and we've got a standoff distance, but also we have other obstacles between the bomb itself and the masonry bomb shelter that we're trying to protect from. We've got hedges. We've got a sacrificial blast wall, and it can be masonry, it can be concrete, or whatever that's designed to fail under extreme loadings. Did you have something you want? You had something you had? Okay, this here is a bomb shelter that's in East Texas that's adjacent to a chemical plant. We talked about the facilities that these bomb shelters are protecting against. This is bomb shelter, and it's using CMU loading, and it's just one level underground. It's got a CMU 12-inch CMU walls and a composite deck roofing system under the massing of the grade surrounding, which is really the offering the protection of the shelter. This is the diagram I was wanting to get to. This shows that I show with my hands well enough that you understand this diagram. This shows explosion going off above grade on the top, and then did you have anything? Then on the second slide is showing the reflected wave coming up and interacting with the incident wave, and then the third slide shows the incident wave, the reflected wave, and the Mach stem propagating outward. Any questions? Do you follow what I'm saying? Okay, I want you to see, this is a video. I might use a mouse. This is a video showing an explosion going off, and I want you to look and see if you can see the incident wave and the reflected wave and the Mach stem, all in this video. Okay, now you see the instant wave right there. Let's do it again. Do you see the instant wave coming? That's the instant wave, and then the reflected wave, and then the Mach stem there at the bottom right. Do you see that? Do it one more time. This is an explosion above grade. It was 20 feet above grade, going off over a hard surface like a parking paving. You have anything you want to add? Okay, in comparison, the design of extreme explosive loading differs from wind loading because through the protection needs to be massing requires robustness of the structure for protecting against blast loading. The buildings require blast resistant materials. You can have different materials to absorb blast loading. You can have sacrificial areas, sacrificial walls that take some of the robustness out of the loading. You can change the geometries. Reflective surfaces we're trying to get away from. We're trying to absorb some of the instant wave, and then the greatest avenue at your disposal is distance. I've said that a number of times. Distance. Okay, so these are some of the avenues that are at your disposal for absorbing some of a blast. The angling of surfaces, unless reflective surface pressures combining with other surfaces. There's the energy absorbing materials. There's polymer coatings that absorb energy. There's ventilation and perforated surfaces. There's masonry walls with openings. There's concrete walls with openings that act like a filter. There's sacrificial areas, layers that I spoke of earlier. There's explosive energy mitigation systems. For instance, you can use an explosion to offset an explosion in the opposite direction. There's distance standoff barriers. That's probably the easiest one to address. There's wave deflection, redirection. There's layering of barriers that I showed you in that slide earlier. There's blast vents and relief systems to control the pressure. There's active mitigation systems, which such as counter explosives to take away the effects of explosions, and more. There's more. So that is a brief. This is a brief because this discussion can go on for hours. But this is a brief discussion of sheltering from dangers, the FEMA P-361 ICC-500 versus DoD shelter for terrorism. Questions? Yes.
1,000 feet. The 10% of what kind of horizontal pressure?
Well, the 4,800 TNT and the 10-off standoff distance was 20 KSI.
Can you proportion it down?
Yeah, you can keep proportion it down. I mean, you can do it linear, but it's not linear. It's not linear, but it's at a point on the curve which is closer to being linear that you can get away with it. Do you follow me? Okay. Any other questions? Please ask questions because I know. Yes, sir. Personally, I don't like it. Personally, I don't like it. Did you want to say something?
Yeah, yeah. But we cannot protect whole building, like blast or tornado. But we can make one room, a very strong room. But it's design. If we try to make whole building, it's very expensive to afford.
But those little one-room bomb shelters are better than nothing, I guess. But usually a lot of times they're under a basement, and that's good. But if they're in a garage, then they got to be NSSA approved, and if they're NSSA approved, then they're good to go. I mean, am I talking to a manufacturer of storm shelters? Yeah. Right. And I don't like it, but that's part of our system. Part of the way we do business. I'm sorry. Are you going to ask me a question? Architect right here. You were talking that you were going to ask me a question earlier. Yeah. Any more questions? Did I address what you came here to learn? Because I had to go through this like I'm shooting bullets because there's so many questions, so many issues to cover. And we've done this a lot. We usually have an hour and a half, but I cut it down and try to get in with basic stuff. I hope I addressed what you intended to come here for.
Well, gentlemen, thank you so much. We appreciate it. As you alluded to earlier, you have an article that summarizes this wonderful presentation. It is out there on the table as you leave. Please grab one, or if you'd like it in a PDF, just let me know. Send that over to you. But the last thing we're going to do is our drawing. Let's see.
Don't look. Don't look.
All righty, we've got Igor Kano. Come on up. All right, folks, thank you. We will see you in 2 weeks for our seminar on resiliency and sustainability in concrete masonry, and update on LEED version 5. Thank you so much.
Good. Thank you. I was planning on your card coming up. You knew that, didn't you?
We can turn off your mic too.
Okay. Sorry.